Hello, I'm Christian Bertsch from Bosch. I am the FMI project leader, and together with other members of the FMI project, I will today present how FMI can be extended by layered standards and how they, together with ASAM standards, enable seamless software-in-the-loop simulation of virtual ECUs. The outline of my talk is as follows. I will first explain the functional mockup interface and its new features in version 3.0. And I will introduce the concept of layered standards on top of the core FMI standards. Then I will present 3 layered standards that have been developed by the FMI project for XCP support, network communication, and structured data. We will see their usage and interoperability demonstrated in 6 different tools. FMI is a free standard to exchange dynamic simulation models between different modeling and simulation tools. It provides an interface description of the model as an XML file and a model representation in the form of binaries or C code, which are then packed into a zip file. Such an entity is called a functional mockup unit. Current maintenance release versions are 2.0.5 and 3.0.2. With more than 200 tools supporting FMI, it is the de facto industry standard for tool-independent model exchange on the system level. The FMI project is formed by about 50 user companies, tool vendors, and research organizations. While FMI 2 is still broadly used, FMI 3, which was released 2 years ago, brings important improvements. These were driven by the advanced usage of FMI in new domains beyond the classical continuous dynamical system simulation, such as virtual ECUs, advanced co-simulation, AI models, and optimization. You can categorize the new features into performance and accuracy improvements, such as event mode in co-simulation, and features for new applications, such as grouping of signals in terminals. And some features belong to both categories, such as clocks to synchronize discrete events, new variable types as needed to represent embedded software, binary variables, and arrays. And very important for today's talk is the preparation for domain-specific extensions in the form of layered standards on top of the core FMI standard. In order to keep the core FMI standard manageable small, we have foreseen in FMI 3 extension mechanisms for new applications. They can be released in form of layered standards on top of the FMI standard and can be defined not only by the FMI project, but by any organization. In the FMI project, we currently develop 4 of them for XCP support, for structured data, network communication, and validation experiments and related files. FMI LS XCP defines support for the XCP protocol from ASAM. The first version of this layered standard was just released this week at the FMI design meeting in Munich. A2L files are packed into the FMU together with a manifest file that describes the capabilities with respect to XCP support. Then a measurement and calibration tool can automatically connect to the FMU representing a virtual ECU instead of the real ECU. FMI LS-Struct is a layered standard for the structuring of variables. Especially it describes how to use several FMI 3 array variables to represent maps that are sampled on rectilinear grids. In 1D and 2D, this corresponds to maps and curves in the corresponding ASAM standard. Also other kinds of variable groups, such as maps on irregular grids, can be defined. The FMI 3 terminals are used for the grouping. FMI LS-Bus describes how to realize network communication for virtual ECUs with FMI 3 features, such as clocks, terminals, and binary variables. Especially the protocols CAN, LIN, FlexRay, and Ethernet can be defined. It uses the given network description files, such as DBC, LDF, FIBEX, or RXML. Two variants have been defined. The high cut uses physical signals and clocks on the transport layers. The low cut defines the emulation of specific bus systems to realize virtualized bus driver implementations. FMUs with FMI LS bus support can be simulated in three ways. On the left, we see the simulation of two virtual ECUs with an idealized bus in a one-to-one connection. This can be simulated in a standard FMI importer without special bus simulation capabilities. To simulate bus effects, two variants are possible. In the middle, we use a bus simulation FMU. With this, a standard FMI importer with no special bus simulation capabilities can be used to simulate bus effects for multiple connected virtual ECUs. On the right, we see a simulation tool with special bus simulation capabilities to simulate the bus effects. On this slide, the current development status of the layered standard is shown. CAN support is currently in beta stage, and we will have a release candidate this year. FlexRay is in alpha stage. For LIN and Ethernet, the development has started. We will now demonstrate the high cut with an example for the closed loop simulation of a fuel injection system with an engine control unit and a transmission control unit. It will be presented by Klaus Schuch from AVL.
Hello, my name is Klaus Schuch from AVL, and I will now show you how to build up a high-cut example in our generic low simulation tool Model Connect, which has a few extensions to support the layered standard for network communication, also called LS-Bus. The example is based on the example that was built up in the Smart Systems Engineering group of ProStep. So I have already started the example here with a vehicle and an engine, and I will now add the first virtual bus component, which is a transmission control unit provided by PMSF. I will connect it directly, this is one possible use case, to the virtual ECU. I use our suggested connections, connect them. The names are not perfectly aligned, so I will connect them manually. Names could have been renamed, but I can also show you how to directly connect it. So the model is now set up, and I can just start a simulation. One of those FMUs is showing log messages, but let's now see the results. Let me reload the results, and you can see the transmission unit created gear shifting points, and we see how the gear shifted. The vehicle speed can also be seen. To show the functionalities of the layered standard better, we will now build the very same example, but with a second FMU that functions as a bus adapter, and so that the normal model is not connected directly to the transmission control unit, but the transmission control unit here connects directly via the bus to the adapter FMU, and we connect this adapter FMU now to the plant model. Can use the suggested connections. Let me reorganize this a bit to have it better looking. So, and the interesting thing here is now what happens in the bus. So those are the bus signals, and all of those bus signals are transmitted at different clocking points. And let's just look at the simulation again. One of those FMUs again gives some output, and we can see after reloading the results, we get the same profile. For more complex models with several FMUs, those direct connections might be confusing. Therefore, we also have the option to create a virtual bus component. I do this just by drag and dropping a DBC file into that, and now I can add the very same ECUs, very same FMUs here again. But I will not connect them directly, but instead connect them via the bus. Let's move those connections over here. So I connect this TCU to the bus, and I connect the ECU to the bus, and connect those to via the suggested connections, acceleration, and equal speed, as before. You can now see the connectivity in the end is basically the same, but the connections are all going through the bus, which in this case is an ideal bus, so there are currently no delays or whatsoever. If I now simulate this, I will get the same results. So the connectivity is just done in a different way, but the simulation in the end is the same. The FMU of this example also supports another layered standard, the layered standard for structuring of data. In this case, the parameters of this FMU can be seen here, and this FMU also exposes lookup tables. FMI on its own cannot represent lookup tables, but with the layered standard LStruct, this can be done. And you can here see several lookup tables for the gear shifts. Such lookup tables are in the A12 standard of ASAM called maps. These parameters can now be set at the beginning of the simulation or even changed during simulation if the FMU supports LSXCP as well, or if like here in this tool, we can expose any tunable parameters of any FMU as via the XCP interface, and then you could connect during runtime and change those parameters if they are tunable. I will not show the XCP during runtime. This will be shown in other demonstrations later on. This was my short presentation of the HiCAD LS bus and a short peek into the LStruct. Thank you for your attention.
Hi, my name is Tim Fitzer from Bosch. I will guide you in the next couple of minutes through our demonstration series. After the showcase of the HiCAD communication, we will focus now on the low-cut implementation of the layered standard. Low-cut in this context means frame level transmission, in this case of the CAN bus. For this purpose, we created a virtual vehicle setup which will show you the flexibility of the FMI and the layered standard for network communication. On the left side of the block diagram, you can find the engine and driver model of the vehicle, which is a standard FMI3 FMU and acts as an environment model. In the middle, you find the main component called controller. This controller is a full-fledged AUTOSAR virtual ECU, including the respective base software components and network stack provided by dSPACE. This includes PDU router, CAN interface, and many more within this FMU. For the layered standard for network communication, a small FMI LS bus driver is built in the FMU and acts as an interface out of the main features of the FMI3 standard for clocks, binary variables, and terminals. As a second communication node, you can find the display provided by Bosch. The display FMU is a REST bus model with a simplified non-AUTOSAR CAN logic, connected also to an FMI LS bus driver. This already demonstrates how the layered standard can be used independent from inner software architecture. Also, the layered standard provides header files, which makes the integration and the usage as easy as possible. The simulation composition of the three FMUs you can see within the block view. Environment model and controller are integrated as closed-loop system, connected via FMI 3 variables. In order to measure internal variables, the controller FMU has also an LSXCP compliant component integrated. The display, in contrast, has no signal communication to the vehicle, and it's only connected via the CAN bus interface. But we are not intend to go into further automotive details of this setup. We would like to demonstrate the seamless tool interoperability across different vendors and the flexibility of the layered standard configuration itself. On the very top you can find the two network FMUs, the controller provided by dSPACE and the display provided by Bosch again. These components will be used now within the demo sessions without regeneration in different setups. Starting on the left. So for use cases where you have only two network nodes, for example, a system under test and a REST bus, we call direct communication. As the name suggests, you can couple them directly with each other, as shown in the picture and later demonstrated by AVL, Altair and Akkodis. If the number of participants increases or you have special requirements to the bus simulation itself, but your simulation tool of choice does not have the required virtual bus functionality, no problem, you can use the virtual bus FMU to create your network, wherein you can model your specific requirements by yourself or vendor of choice. Also here we will see AVL and Altair using a simplified bus FMU crafted from the FMI group. But we will now start our demonstration series with the third use case, where dSPACE and SYNOPSYS showing how their tool have an integrated virtual bus solution, having access to the bus traffic and can manage as well as route them through the FMI LS bus interface. In this first part of the demonstration, the AutoSAR configuration and the export of the controller artifact will be shown with the dSPACE toolchain. After the generation, all of the components will be integrated, simulated and measured within the dSPACE simulation environment. The setup is connected via an integrated virtual bus simulation, which is compliant with the low-cut standard.
In the next few minutes, I will show you how the presented showcase can be realized by using the dSPACE toolchain for virtual validation. For this, we will firstly create the controller VCU FMU with dSPACE System Desk. After this, we will integrate the complete simulation system with all artifacts by using dSPACE VEOS. And last but not least, we will use dSPACE Control Desk to show that the whole simulation system works as expected. So let's start creating our controller VCU FMU by using dSPACE System Desk. I already import AutoSAR data and create a system where the application software we want to use in our showcase is mapped. We also see that our ECUs and our network topology is already created. I also already added the AutoSAR basic software modules, which shall be used within the VCU FMU. By using System Desk, you can automatically auto-configure and generate each of them. So for example, if we are opening the CAN module, then we see that System is automatically updated and generate FMI LS bus compatible code for it. So you don't have to do something by hand. The same is done for the XCP module. In the next step, we will export the VCU FMU from System Desk. For this, we export the FMU, select the specified platform we wish, and after this, it will be automatically built for us. So if the build is finished, then we can look inside the FMU and see which artifacts are generated. We can now open the FMU which was generated by SystemNest by using a simple zip tool. We see inside that there is an FMI 3.0 compatible FMU, which also includes the layered standard for XCP and also the layered standard for network communication. To simulate the whole system, we had to import the simulation artifacts into VEOS first. If there is included an FMI LS XCP, you can also configure it during the import of the FMU into VEOS. Now the controller FMU is been imported, and we had to import the second ECU FMU. VEOS automatically detects that each FMU we imported has included an FMI LS bus, so you can directly connect it via the bus feature set of VEOS. Now we have to import our environment module, which is called engine model, for our simulation system. So after the import is finished, we have to connect the FMU variables of the environment model to the FMU variables of the controller VCU FMU. Now everything is prepared and we can start our simulation. After we start the simulation, we could use dSPACE controllers to measure and calibrate the specified A2L variables that are provided by the FMI LS XCP. For this, we start the measuring. And after the measuring starts, we'll firstly see the bus traffic that happens within the whole simulation system. And also we see the measurements of the A2L variables.
Now SYNOPSYS will follow, showing how to connect and simulate the same artifacts without reconfiguration or generation. Therefore, the SYNOPSYS simulation environment, also with an integrated virtual bus simulation, will be used. This will also demonstrate the interface independence of the layered standard from different tool and virtual bus vendors.
Welcome to the SYNOPSYS demonstration of SIL's generic FMI3 support. We focus on the layered standards for buses, LS bus, and for XCP, LS XCP that will be introduced in future SIL versions. The main purpose of this demo is to illustrate how external FMUs can be easily co-simulated with Silver. The shown setup features 3 participants of different origins, an engine model and a controller from dSPACE, and a display model that has been provided by Bosch. Engine and controller are coupled by a default signal interface, and the controller and the display are coupled by a low-cut LS bus CAN indicated by the red arc above in the picture. The implementation is straightforward. Choose Silver's FMU CS30 module and point to the FMU of interest, as illustrated here on the engine model. Let's get the simulation running. Naturally, some signals are not yet connected properly, so we should implement rename rules or just map interactively in the GUI. Notice that no red cross remains on once everything has been connected. Now that these signals are connected, we can check how the controller and the engine co-simulate. Therefore, we can check, for instance, the fuel rate, and we can see that there are interactions between the engine and controller. The fuel rate of the controller is plotted above, and the engine throttle value is plotted below. Now let's focus next on LS bus. Let's have a look on the LS bus implementation between the controller and the display now. We start the simulation, and one can see there are no real inputs between the controller and the display. Messages are relayed through the Silver's own SVB CAN bus implementation for the LS bus. With the bus monitor active, we can log messages to our console. Inside the console, we can see the timestamp, the sender, and the payload. Of course, we can also check the signals received on the display directly. Let's have a look. Here in yellow, we see the original signal, and in blue, the received one via LS bus. And one can even see the bus stereo artifacts based on the transmission. Finally, let's focus on XCP, which the controller has equipped as well. That means internal labels can be accessed via XCP communication. There are easier ways to access A2L labels of a module in Silver, but for the sake of demonstration, we take our XCP master module in this case. But first, we need to tell Silver's module the correct configuration. Okay, TCP localhost and port 44001 is correct. That's fine. Now let's activate it, and we can compare here one signal that is exposed, which is called throttle. The purple one is the received signal, and the yellow one is the original. And as you can see, the shape is very, very similar. This completes Silver's FMI 3 demonstration. I thank you for watching.
Akkodis will now focus on the XCP measurement use case alone, showing that the FMUs can be used in different contexts and for different use cases. Therefore, the LSXCP compliant component within the controller will be used to measure and calibrate internal variables.
Hello everybody, my name is Kahraman Jumayev. Today I present FMI layer standard for ASAM XCP protocol with PRUTEC toolsuite from Akkodis. Here's a general overview about PRUTEC toolsuite and demo. PRUTEC supports all of the FMU models based on new FMI and FMI layer standards for virtual testing and validations. To demonstrate this showcase, I use a controller virtuality FMU exported by dSPACE system desk tool, and this FMU has an integrated XCP service and implemented according to FMI layer standards for XCP. The goal is to show how to configure and import such FMUs into PRUTEC runtime environment and make a measurement and calibration with XCP protocol or IP using PRUTEC TA test automation tool. Let's get started with real demos. The configuration of the virtuality FMU is rather simple. It's XML based and it's loaded as a normal FMU model into the tool. And the XCP settings is also straightforward. We have set the path to A2L file and choose the transport protocol, TCP or UDP, and start the rest with default settings. So once we loaded the model, all variables and parameters from the A2L file and from the FMU model description file registered as a signals, just like any other signal of your hardware in the loop or software in the loop system. Additionally, we have a tool-specific signals to start the simulation, run it continuously, or run it in single steps, similarly to start or stop the measurement. Now let's measure some signals from our controller virtuality FMU and start the XCP communication. For that, we need to add some model signals into the measurement. It's possible multi-rate measurement of the signals and start the data acquisition and run the model. So now we see the signals measurement values also in the chart controls as plots. And the message window shows the communication between the XCP master and the XCP slave inside the controller virtuality FMU. Similarly, we can stop the XCP communication and start again, stop the data acquisition, and save it into the file for further analysis. So this is short and very high level overview about FMI layer standard for XCP with PRUTEC toolsuite. Thank you very much for your attention.
Now ABL will show the missing two low-cut configurations within their tool. In the first part, the direct communication use case will be shown where the CAN frames will be directly transmitted between the two FMUs. And in the second step, the setup will be enhanced with a so-called bus FMU, which acts as a routing module.
Hello, I'm Klaus Schuch from AVL. I will now show you how the low-cut example can be set up in our generic co-simulation tool Model Connect, which has a few extensions to support the layer standard for network communication. For this, I will take the FMUs that were generated in previous videos. First, the FMU created by dSPACE, which represents a controller. Then I had the FMU created by Bosch, which represents the display, and the display and the controller get connected via the bus. I can connect them directly. You see that based on the matching rule of the layered standard, the clocks and the data ports are connected automatically. Now I can connect the engine to the controller. For this I will use our bundle connector. Take the suggested connections. Since the names are similar, I can take those and use those connections. I will just move this port so that it looks a bit nicer. And now I can simulate the model. On the right hand side, you see the log file, and on the left side, you see the simulation output directly of a few signals. One of those FMUs, the display FMU, was configured to send warnings with the actual content. This is just here done for debugging. You see that the CAN frames get sent. We can now have a quick look into the results, and already zoomed in here, and you can see typical effects of CAN bus communication, where we have sampling effects, for example, here. For more complex examples, direct connections are not always possible, and we need something like a bus simulation FMU. I will show this now as well. I will add a bus simulation FMU, the same controller as before, and also the display as before. Now I connect the controller to the first node of the bus, connect the display to the bus FMU, and I connect the controller to the engine. And now I can have a quick look at the connections that were done, again by matching rules to the first node and to the second node. And if I simulate this now, I will get the same results before, because the bus simulation FMU was configured to simulate no delays and also no bus failure. We look at the results, and if I zoom in here, we see very similar sampling effects as before. Okay, thank you. This was my presentation of how the low-cut FMUs can be simulated in Model Connect. Thank you for your attention.
The demonstration will be completed with a presentation of Altair, wherein the direct as well as the bus FMU use case will be shown. Please keep in mind, across all demonstrations, we use the exact same artifacts, which demonstrates the interoperability of tool vendors, configuration, and even use cases.
Hello everyone, I'm Masoud Najafi from Altair, and I'm going to present Altair Twin Activate for the simulation of FMI LS-Bus, or latest standard for network communication. Twin Activate is a general-purpose tool for modeling and simulation. This tool is a general tool, and there is no specific support for automotive buses or XCP standards. FMI LS-Bus, or latest standard for network communication, is a standard based on the FMI standard, which means that any LS-Bus FMU should comply the FMI standard. So any tool supporting the FMI standard should be able to simulate these FMUs. Twin Activate supports the FMI standard, and in particular clocks and the binary data type, which is sufficient for the simulation of LS-Bus FMUs. In this presentation, Twin Activate is used for simulation of these FMUs for low-cut connections. Twin Activate is a general-purpose tool that any system can be simulated with this tool. For example, this is a model for the simulation of a hydraulic system. And this is a model for simulation of an electrical system. The first demo shows the simulation of 3 LS-Bus FMUs. with low-cut variant using direct connections. There are three FMUs, an engine model, an engine controller provided by dSPACE, and another FMU to display the CAN bus data provided by Bosch. These FMUs are connected either with physical signals like this one. This is the feedback signal, fuel rate, fed to the engine model, or data connections, the CAN bus data connections, which is binary data to transmit the CAN bus data from controller to the display FMU, and also the clock link for synchronization purposes. If we run the simulation, we can see the signals on the engine side, the physical signals, and also the signals read from the CAN bus and displayed by the display FMU. The second demo is also for the LS bus with low-cut variant, but this time instead of direct connection between the FMUs, the controller and the display FMU, we use an FMU which simulates the bus connection. This FMU receives data from the controller, the CAN bus data, and the clock for synchronization purposes, this red link, and retransmit this data to the display FMU. If we do the simulation, we see that in the scope, we signal at the engine side, and at the right-hand side, there's signal read from the bus FMU.
Already the core FMI standard can be used for the simulation of simple virtual ECUs. For more advanced simulation, this is not sufficient, but can be extended by layered standards that make use of FMI3 features. And the FMI project has defined 3 of them to enable XCP support, network communication, and structured data such as maps. The benefit is to lower integration costs through better interoperability and more efficient collaboration through significantly reduced coordination effort. This will be a revolution for SiL simulation of virtual ECUs. Thank you for your attention and contact us in case of questions.